Now we're going to look at an equation where we're driving a pendulum, but I'm going to actually put a pendulum out here in front of you, and I recommend that you do this yourself. Okay, now here's a pendulum. If I start driving this pendulum with a force just by moving my fingers back and forth, not too much happens if I don't drive this thing at just the right frequency. But if I do drive it at the right frequency, then just a small motion of my fingers will keep this thing moving. If I speed it up a little bit, well, I lose it again. If I slow it down, eventually I get to the point where I do have a resonance. If I slow it too much, well, that's going to be a little more difficult to demonstrate. But you understand that if I don't drive this thing at just the right frequency, it's not going to oscillate very well. The applied force, the force I was applying, was probably a pretty good approximation of a sine or cosine function. Increasing in this direction, then decreasing, then increasing in this direction, decreasing. So let's assume an applied force of the form F cosine of omega 1t, where omega 1 is the angular frequency of my force. Now remember, there's a natural frequency, omega naught, equal to the square root of k over m, with which the system wants to oscillate, and I'm driving it with some force that has an angular frequency omega 1 that might or might not be close to the natural frequency of the system. The equation becomes net force, mass times acceleration, mx double prime, negative kx. The restoring force is still there no matter what I'm doing, plus the force that I'm applying. So this equation rearranges in the obvious manner, and if I divide through by m, I'll get a k over m here, which is the square of our omega naught being equal to the square root of k over m. And over here I get an f over m times the cosine of omega 1t. Now this is practically identical to the problem that's solved in the current edition of the textbook. So I do want to draw your attention to one little difference. The solution in your textbook just calls this coefficient here f, and doesn't develop it from a force here. And of course f stands for just a constant. F of t stands for a function. Okay, and we've replaced the f of t function with this expression. I think it's important to use f over m here to remind ourselves of the physical meaning of the terms. So I'm going to use f over m where your book just uses an f here. And if you know the physics, you'll understand why I'm doing that. If you don't understand, you can simply accept it. A little difference in notation. Okay, well, here's our equation. We have a fundamental set for the characteristic equation, the homogeneous equation. That's cosine of omega naught t, sine of omega naught t. We're very familiar with that. So our characteristic solution is this familiar solution that we've seen already. Now, what are we going to do for the particular solution? The right-hand side, the non-homogeneous term in this equation, is a cosine term. We have some constant times the cosine, but it's a cosine term, so it would be natural to use a particular solution of the form a cosine of omega 1t plus b sine of omega 1t, simply because we're combining derivatives of this function, and I just noticed that I'm calling this function y here where I'm using x here, and I'll have to correct that in a second. Anyhow, you understand that our derivatives of this function are going to be such that they combine to give us sines and cosines of omega 1t, and if we adjust our parameters a and b, our coefficients a and b, we could end up with the function f over m cosine omega 1t when we run this function through the equation. Okay, I've made the correction. Now, in order to plug this solution into the equation, I've got to find my x double prime, which is going to be very easy to do. I'm simply going to write it down. We've already done a number of solutions of similar equations. So there's our x double prime. Now when we plug this back into our equation is going to become what? Well, it's going to be omega 1 squared a cosine of omega 1t, and I'd better put my negative on there before I forget, minus omega 1 squared b sine of omega 1t plus omega naught squared multiplied by just our xp function, which is a cosine of omega 1t plus b sine of omega 1t. And that, when we combine it all together, is going to give us negative omega 1 squared plus omega naught squared times a cosine of omega 1t plus the same coefficient, negative omega 1 squared plus omega naught squared times b sine of omega 1t. Thought I'd mix that up. And that's going to have to be equal to our f over m cosine of omega 1t. Clearly then, the coefficient of the cosine is going to have to be f over m, which means that negative omega 1 squared plus omega naught squared times a is going to equal f over m, so that we get a equals, I'll write it this way, f over m divided by omega naught squared minus omega 1 squared. And b equals 0 because we have no sine function, no sine term on the right hand side. This implies that xp of t should equal f over m divided by omega naught squared minus omega 1 squared times the cosine of omega 1t. So that our x of t function, which is going to be a sum of the characteristic and particular solutions, will end up being c1 sine of omega naught t plus c2 cosine of omega naught t plus f over m times omega naught squared minus omega 1 squared cosine of omega 1t. Now, this is going to be identical to the solution you'll probably see in your textbook. And this is, of course, a very standard problem that's done, I would guess, in the majority of introductory differential equation textbooks. The only difference between the book solution and mine is I have the f over m where they just have the f. And nothing against them using just the f, but I prefer to use the f over m because I think it's very important to keep track of the meanings and the units of various terms.